Hello there, and welcome to Whispers of Earth, the place where curiosity settles in like an old friend and even the strangest ideas somehow feel at home. Tonight, we're traveling somewhere older than story, older than language, older than the word old itself ever meant anything. Not out into the stars, not into dreams, but backward. Far backward. Not just before your grandparents, or before pyramids, or before the first flicker of paint on a cave wall. Before humans. Before mammals. Before dinosaurs even dreamed of scales. Before nearly anything that carried a spine. We're going to wander across an Earth that existed before we did, before we could even be imagined, and meet the lives that ruled it, reshaped it, and, like all things, eventually disappeared. This is the sort of journey that deserves a soft blanket, a quiet room, and maybe the faint groan of time itself winding in reverse. Wherever you are, at home, in bed, outside under a slow sky, pause for a second and look around. Your floor, your window, the screen in front of you, even your own hands, every bit of it is new. Not just new in the modern sense, but geologically newborn. Your house, the road outside, the species you belong to, they're all flickers at the tail end of a story stretching billions of years behind you. And the characters that filled the earlier chapters. They weren't human. They weren't close. So tonight, let's slow things down. Let's peel back the layers of time without hurry. You don't need to memorize names or dates, just let the planet reveal itself one stratum at a time. After all, Earth has nothing but time to give. If you could hit rewind, not by years or centuries, but by millions of years per heartbeat, the surface would shift faster than your eyes could track. Forests would vanish in seconds. Oceans would drain and swell. Mountains would crumble back into dust and rise again from molten wounds. Cities would blink out, one instant of light, then gone, replaced by ice, then tundra, then emptiness. Animals would appear and vanish like passing thoughts. Even the continents wouldn't stay put, they'd drift and twist like puzzle pieces floating in syrup. And beneath that chaos, deeper than all the noise, something stranger would be unfolding. The further backward we go, the less familiar life becomes. First it looks odd, then alien, then almost invisible. Life took its time. And it certainly didn't start with us. Our earliest ancestors weren't people or animals, they were chemistry. Simple molecules colliding in shallow pools, trying every combination they could. Most attempts failed. A few managed to linger. The ones that stuck around slowly learned the art of staying. But before we meet the winners, the dinosaurs, the mammals, and the thin, curious branch that leads to you and me, we have to ask the simplest question: what counts as life? Go back far enough and the answer blurs. We like to think of living things as creatures that move, breathe, eat, but that's not where it began. Life began small. Inconceivably small. Not just microscopic, but nearly invisible even to the best lenses we've ever built. Early life didn't think. It didn't hunt. It reacted, it copied, it failed, and occasionally that failure invented something new. Earth itself wasn't an easy host. For a long time it was violently unwelcoming. Fire breathed from its lungs, acid fell from its clouds, and asteroids arrived far too often for comfort. Yet in some shaded corner of a young ocean, something began. Not a fish, not even a cell, but a pattern, a way of arranging atoms that could make more of itself. The first replicating molecules. They weren't alive the way we define life now, but they were the start, a story told with no storyteller, a rhythm repeating only because physics allowed it. Even that was enough. In time, these chemical patterns learned to build fragile walls, membranes, tiny bubbles separating inside from out. Those bubbles became the earliest cells, and that changed everything. The first real citizens of Earth weren't animals or plants, they were bacteria, specifically, prokaryotes, single-celled beings with no nucleus, thriving in water, feeding on the chemicals around them, dividing endlessly. They didn't build cities or write music. They didn't walk or fly. But they were everywhere, and for more than 1 billion years, they were all there was. That's the part we tend to forget. For most of Earth's history, nothing had a face, no eyes, no teeth, no thoughts, just microbes. You could wander millions of years in any direction and never meet anything larger than a speck of dust. But small didn't mean boring. Quite the opposite. Those tiny pioneers were rewriting the planet. Some of them learned to feast on light, not with eyes, but with chemistry. They discovered photosynthesis, turning sunlight into food. A harmless-sounding trick that changed everything, because in doing so they released oxygen, an element so reactive it was poison to nearly all life that existed. When those light-eaters started pumping oxygen into the oceans and sky, they triggered one of the first mass extinctions in Earth's story. We call it the Great Oxidation Event, and it nearly erased life completely. The seas rusted red as iron reacted with oxygen. Microbes that had never met the gas suffocated by the trillions. And yet, out of that catastrophe came invention, cells that not only endured oxygen but harnessed it. They became the ancestors of all complex life, including us. That leap from simple to complex didn't happen in an afternoon. Roughly 2 billion years ago, one cell engulfed another, and instead of digesting it, formed an alliance. The guest cell became a mitochondrion, a tiny power station producing energy with stunning efficiency. From that partnership arose the eukaryotes, cells with internal architecture, with a nucleus at the core. Every plant, every animal, every fungus traces back to that single, improbable moment of cooperation. Once complexity had a foothold, the story accelerated. Multicellular life followed, colonies of cells that stayed together. At first, they were shapeless clusters. No nerves, no organs, no plan. But specialization crept in, some cells for motion, others for feeding, others for reproduction. That division of labor led to the earliest animals, soft, slow, strange creatures that left little fossil trace. Some, like the enigmatic ediacaran forms, still puzzle scientists today. They had no mouths, no symmetry, maybe no true movement at all. Yet they paved the way. Then, about 541 million years ago, life erupted in diversity and complexity. The Cambrian explosion wasn't a blast of fire, but a bloom of form and function. New species, new strategies, new body plans filled the seas. Predation began in earnest. Eyes appeared. Armor, spines, shells, all the hallmarks of an evolutionary arms race. Trilobites, armored arthropods, scuttled along the seafloor. Anomalocaris, a predator with stalked eyes and grasping limbs, ruled the open water. Sponges filtered the currents, worm-like burrowers tunneled through sediment. None of these creatures would see the modern day, but their blueprints echo in the life around us. Ecosystems formed. Food chains tangled. Evolution gathered speed, and never slowed again. Still, all of this drama remained beneath the waves. For hundreds of millions of years after the Cambrian, the land stayed untouched, a dry crust, lifeless not because it couldn't support life, but because nothing had yet solved the puzzles of dryness and sunlight. The oceans remained safer, easier. Eventually, though, the first to dare weren't animals but plants, or rather, their ancestors. But that's for later. Before roots ever gripped soil or legs touched ground, the sea had more stories to tell. Before life, there was only a planet, not calm, but alive in a different way. If you could visit Earth in its first days, you wouldn't recognize it. You couldn't breathe, couldn't stand, couldn't survive a heartbeat. Yet this was home, long before anything could call it that. Roll time back 4.5 billion years. Earth was born from a swirling cloud of dust and gas around a young sun. Rocks and metal fragments slammed together in a cosmic construction site that raged for tens of millions of years. Collisions were constant, some small, some planet-sized. One of those colossal impacts likely involved a Mars-sized body striking Earth, scattering debris that eventually gathered into the Moon, the pale scar still hanging above us, a souvenir of planetary trauma. After that chaos, Earth didn't settle quickly. It was a furnace, molten rock, seas of lava, an atmosphere thick with choking gases. No continents yet, no oceans, just crust forming and cracking like a puzzle refusing to stay solved. But over ages, the surface cooled. Steam condensed. Rain fell, not gentle rain, but storms lasting centuries, filling basins, carving valleys, creating the first oceans. That water came partly from deep within, released as the planet cooled, and partly from icy comets carrying moisture across the solar system. The air above was nothing like ours, no oxygen, but carbon dioxide, nitrogen, ammonia, methane. Lightning tore through the sky, ultraviolet radiation bathed the surface. Unlivable to us, but perfect for chemistry. Scientists call it the prebiotic Earth, a world without biology but rich in possibility. Warm pools, volcanic vents, mineral-lined shores, all simmering with energy. And somewhere in that restless mix, the first whispers of life began. Not a creature, not even a cell, but a process. Before anything could live, something had to copy itself. Molecules bumped and joined and split until, by chance, a few could make rough replicas. It sounds impossibly unlikely, but given billions of molecules and millions of years, even the improbable becomes inevitable. One idea, the RNA world hypothesis, suggests that simple RNA molecules, cousins of DNA, formed by chance in those early waters. RNA can store information and even catalyze reactions. Some may have learned to copy fragments of themselves, kickstarting evolution's slow crawl. Another idea points to hydrothermal vents, deep-sea geysers spewing hot, mineral-rich water. They offered energy, surfaces, and chemical gradients ideal for experimentation. Perhaps there, in darkness lit only by the glow of magma, chemistry tiptoed into biology. However it happened, persistence won. Some molecules became better at copying, others built protective shells, membranes, to guard what mattered. The first cells emerged, simple, fragile, alone, but no longer passive. They used energy, they grew, they divided. Life had begun, quietly, invisibly, but without pause. If you stood on Earth then, you'd need a suit thicker than any we could make, you wouldn't notice the change. No forests, no fish, nothing larger than a speck. Yet in those young oceans, the rules of the planet had changed. The story now had characters, even if microscopic ones. These first cells, our ancestors, were prokaryotes, mostly bacteria. They had no nucleus, no complex machinery, but they were masters of endurance. They ate chemicals, floated and clustered, drifted through currents. Soon they diversified, some learned new diets, others new tricks, like capturing sunlight. Photosynthesis didn't just feed them, it transformed the world. The earliest oxygen producers weren't plants but cyanobacteria, blue-green microbes turning sunlight, water, and carbon dioxide into food, and exhaling oxygen as waste. At first, that oxygen met iron in the oceans, rusting it into layers that settled on the seafloor. But eventually, oxygen began to build in the air, and for most existing life, that was lethal. Oxygen tore molecules apart. It poisoned cells unprepared for it. As levels rose, countless species vanished. Yet life adapted again. Some microbes evolved defenses, others learned to breathe the poison. This slow transformation, the Great Oxidation Event, lasted hundreds of millions of years. It wasn't one catastrophe but a long, uneasy shift that remade the sky, the seas, and the possibilities of evolution. During this time, continents began to gather and drift. Volcanoes built mountains, erosion ground them down. The crust never stopped moving, and life followed those changes wherever it could. Fossil traces from this age are rare, single cells don't leave bones, but they left monuments of another kind, stromatolites, layered mounds built by microbial mats trapping sediment, still alive today in places like Shark Bay, Australia. Slow, stubborn, quietly shaping their world one layer at a time. Back then, Earth spun faster, days lasted 18 hours. The moon hung closer, tides pulled harder. Weather was wild and alien. But life persisted, refined its tools, and waited. It would be easy to call those eons slow, but that patience was foundation building. Genetic codes, energy systems, and cellular structures were all being tuned for what came next. Earth was still a microbial world, and microbes were thriving just fine, no eyes, no legs, no hurry. Eventually, complexity stirred again. Cells learned cooperation, multicellularity emerged. Evolution isn't planning, it's trial, error, and the occasional brilliant accident. And while oceans remained the center of the story, everything was quietly setting up for the chapters to come. If you could drift through the oceans 3.5 billion years ago, you wouldn't hear much, no birds, no waves against beaches, not even the rustle of leaves. Silence wouldn't just be the absence of noise, it would be the absence of things that could make noise. No wings, no footsteps, no breath. The world was moving, but it moved unseen. Volcanoes boiled the seas. Tides slammed against bare rock. Meteors burned through the sky and vanished into the dark water. No one witnessed it, no one named it, but all of it was happening under the same rules that still hold today: heat, gravity, chemistry, and time. Yet in the shallow waters hugging the young continents, something astonishing was already underway. If you looked closely enough, through the haze of minerals and mud, you'd find colonies of microbes clinging to rock, nesting in grains of sand, floating in the shafts of sunlight that pierced the water's surface. They had no eyes, no nerves, no sense of the vastness around them, but they were busy beyond belief. These were Earth's first true communities, woven from bacteria and archaea, single-celled pioneers who together built the foundation for everything that followed. For more than 2 billion years they were the planet's only inhabitants, and during that immense stretch of time they didn't just survive, they transformed their home. Early cells drew energy from whatever chemistry surrounded them. Some fed on hydrogen, others on sulfur, iron, or methane. They flourished in conditions that would kill almost everything alive today: acidic pools, boiling vents, freezing brine. We now call their modern descendants extremophiles, but back then such extremes were simply normal. Without predators or plants or competition, these microbes covered almost every wet surface on Earth, spreading across the seafloor, thriving inside porous stone, and forming dense mats that rippled in the current like living carpets. Within those mats, life organized itself in miniature societies. One species' waste became another's food. Some layers handled the flow of nutrients, others recycled what had been used. They weren't aware of one another, but they cooperated perfectly through chemistry alone. These were the earliest ecosystems, tiny self-sustaining worlds built cell by cell. And then, a new ability changed everything again: photosynthesis. At first it wasn't the green-leafed kind we know today. Early microbes used other molecules, hydrogen sulfide, for example, to harvest light and store energy. It gave them a clear advantage wherever sunlight reached. But eventually a lineage of these microbes stumbled upon a more powerful trick: using water as their raw material. That discovery created oxygen as a byproduct, and with it, the planet's first true revolution. The inventors of this process were cyanobacteria, the blue-green architects of our atmosphere. They multiplied in shallow seas, spreading over tidal flats in thick layers. Each layer produced more oxygen, and at first, all that oxygen reacted with dissolved iron in the water, forming rust that sank to the bottom. Those ancient chemical reactions are still visible today as banded iron formations, striped rocks recording the moment life changed the chemistry of the world. Eventually, the oceans could absorb no more, and oxygen began to escape into the air. For most organisms alive then, it was toxic. Oxygen ripped apart delicate molecules, damaged proteins, and shredded DNA. It was the first great environmental disaster, the Great Oxidation Event, and it unfolded over millions of years. Populations collapsed. Entire microbial networks vanished. But even as some died, others adapted. A few learned not just to survive oxygen but to use it, turning poison into power. That discovery, aerobic respiration, released far more energy from food than any previous chemistry. Cells that mastered it could move faster, build stronger structures, and store more information. They became the architects of a new biological order. The consequences rippled far beyond the microscopic. Oxygen altered the color of the sky, reshaped the minerals of the crust, and eventually formed an ozone layer high above, shielding the surface from ultraviolet radiation. For the first time, parts of the planet began to grow truly habitable for complex life, though that complexity was still a distant promise. Through all these changes, microbes remained the planet's rulers. They learned to trade genes, share useful mutations, and form spores to wait out harsh seasons. They lived in colonies, films, and bubbles. They were flexible, inventive, relentless. Even without nervous systems, they could sense chemical gradients, moving toward food and away from danger. Within their mats they built structure, ridges, domes, pillars, patterns that shaped currents and trapped sediment. Over generations, those patterns hardened into stone. These ancient microbial skyscrapers are known as stromatolites. They dot the oldest rocks on Earth, layered, rippled monuments to life that worked not with hands but with time. Each layer marks a community rising over the remains of the previous one. They didn't plan, they didn't design, yet they built landscapes that lasted billions of years. Stromatolites were everywhere in those early oceans. Coastlines glittered with them. They turned tidal flats into textured mosaics. As they grew, they reshaped the seafloor, slowed erosion, trapped nutrients, and quietly produced more oxygen. In doing so, they became both the sculptors and the storytellers of early Earth. The world they built was strange. Days lasted barely 18 hours, the moon hovered closer, pulling giant tides across shallow seas. Weather swung wildly as volcanoes coughed ash into a thick, reddish atmosphere. But beneath all that drama, life carried on, layer after layer, cycle after cycle. Each generation inherited a slightly improved version of itself, and over unfathomable spans of time, the machinery of biology grew more precise. The line between simple and complex slowly blurred. Some microbes began to form internal compartments. A few developed scaffolds to hold enzymes in place. Others started storing genetic material more securely. These weren't leaps made in a moment, they were gradual refinements, experiments repeated countless times until one worked better than the rest. Then came another partnership that would change everything: endosymbiosis. Somewhere in the ancient sea, a large cell engulfed a smaller one, not as prey, but as a tenant. Instead of being digested, the smaller cell offered its host something extraordinary: efficient energy production. In return, it gained protection. That quiet cooperation gave rise to the first eukaryotic cells, life forms with nuclei, mitochondria, and internal organization. Every creature you can see with your eyes today, from mushrooms to whales, descends from that one improbable alliance. It was biology's first great merger, and it opened the door to size, shape, and diversity on a scale the planet had never known. Still, Earth remained a microbial world for ages after. Even as eukaryotes emerged, most of the planet's biomass belonged to bacteria and archaea. They occupied every corner: hot vents, salt flats, frozen lakes, deep rock layers. They were the unseen engineers of the planet's chemistry, producing gases, cycling elements, creating the conditions under which larger life would one day thrive. Modern scientists sometimes call the billion years that followed the Great Oxidation the boring billion, but the name is misleading. It wasn't boring at all. It was a period of quiet innovation. Cells were fine-tuning their engines, experimenting with new internal parts, discovering how to cooperate. Oxygen levels rose and fell, ice ages came and went. Every fluctuation nudged evolution forward, teaching life how to handle change. Through these endless ages, the atmosphere thickened with the breath of microbes. Continents drifted, colliding to form supercontinents like Nuna and Rodinia, only to split apart again. Each rearrangement stirred the oceans, mixing nutrients, spreading species, and driving new adaptations. Under the surface, life pulsed in unseen rhythms, patiently setting the stage for everything to come. If you could peer into those ancient waters, you'd see mats of color: green, orange, violet, each hue representing different pigments tuned to capture different wavelengths of sunlight. Some microbes burrowed into sediment to escape oxygen's sting. Others floated freely, blooming and fading with the seasons. Everywhere, microscopic activity was building something immense: the biosphere. When we think of architects, we imagine intention, plans, designs, blueprints. But the first architects of Earth had none of that. They worked by accident, by repetition, by survival. Each reaction, each replication left the world slightly changed. They created new minerals, altered the balance of gases, and paved the way for creatures that would someday marvel at their work. Eventually, as oxygen stabilized and the ozone layer thickened, sunlight reaching the surface grew gentler. The upper ocean became a playground for new possibilities. Some cells formed chains, others flattened into sheets. A few began to share genetic information in more controlled ways, synchronizing division, communicating through chemical signals. It was the faint beginning of collective behavior, the seed of multicellularity. These early collaborations weren't planned unions, they were accidents that happened to persist. When sticking together provided an advantage, protection, stability, or efficiency, the trait was passed on. And with time, colonies of cells began to behave almost like single organisms, dividing labor among themselves. Movement, feeding, reproduction, all became shared responsibilities. This new complexity set the stage for the next burst of innovation, but the ocean still belonged to microbes. Even now, after billions of years, they remain the planet's most successful life forms, by number, by weight, by endurance. There are more bacterial cells in your own body than human ones. They were here first, and they never left. The earth they built was ready. Oxygen hung in the air, nutrients cycled through water and rock, and energy flowed freely between living and non-living systems. The rules of biology had matured. The stage was prepared for larger actors to enter, creatures that could move, hunt, sense, and think. But before that curtain rose, the world of microbes had one more masterpiece to offer, the transition from single cells to true multicellular life. It wouldn't happen quickly. It would take more than patience, billions of small experiments, a trillion generations of trial and error. But when it did, the change would be irreversible. The planet that once echoed only with silence would soon teem with sound, color, and motion. The quiet architects would pass the torch to a new caste of builders, each carrying within them the memory of those first, unseeable beginnings. For billions of years, Earth followed a single melody, one sung in whispers by cells too small to see. They floated, divided, merged, and adapted in patterns that stretched across ages. Nothing hurried them. Nothing needed to. Then, after a patience almost beyond comprehension, a new rhythm began to pulse beneath the waves. Some cells started sticking together. Not accidentally, but purposefully, though purpose then only meant that it worked. At first, these were simple colonies, little more than clusters sharing nutrients and space. Yet even that tiny step altered evolution forever. Once life discovered the benefits of teamwork, the door to complexity swung open. In these early cooperative mats, a few cells specialized. Some gathered energy, others focused on repair or reproduction. Division of labor was born. At first the arrangement was fragile, a broken bond or a bit of turbulence could scatter the group. But stability brought advantages, better defenses, better survival, and nature rewarded the pattern. For eons this quiet refinement continued. The oceans grew richer in chemistry, the air thicker with oxygen, the ozone stronger overhead. Energy flowed more freely, and life began experimenting with size and shape. Tiny filaments, hollow spheres, gelatinous sheets, all trying new ways of being alive. Multicellularity wasn't a single invention, it was rediscovered again and again, in countless lineages. Most vanished without trace. A few endured, and in their endurance they sculpted the path toward everything that would follow. By roughly 600 million years ago, the seas were no longer empty deserts. Soft-bodied organisms drifted and crept along the seafloor, leaving faint impressions in the mud. They had no bones, no shells, just simple tissues arranged in unfamiliar forms, leaf-shaped bodies, quilted surfaces, branching fronds. We know them today as the Ediacaran biota, and they remain one of evolution's great puzzles. Some resembled plants, others jellyfish, others nothing at all. They absorbed nutrients directly through their skin and reproduced by releasing clouds of spores into the water. Then, after tens of millions of years, they disappeared. No one knows exactly why, perhaps changing oxygen levels, perhaps predation, perhaps the arrival of something new. Because not long after their vanishing, the world woke up. Around 541 million years ago, in what would later be called the Cambrian period, life accelerated. In the geological blink of about 20 million years, diversity exploded. New body plans appeared faster than the rocks could record them. Organisms learned to burrow, crawl, swim, hunt, and hide. It was as though evolution, long content to hum softly, had suddenly found its voice and begun to shout. We call it the Cambrian explosion, though it wasn't an explosion of fire, but of possibility. Animals developed skeletons and shells, predators gained jaws, prey invented armor. The simple world of microbial mats and gentle grazers transformed into a stage crowded with movement and intent. Before this time, nearly every creature had been soft and slow, filtering food from the water or absorbing it from the seafloor. Now, the oceans teemed with strategies. One organism chased another. The eaten became the hunter. Speed mattered. Vision mattered. Decisions mattered. Among the first stars of this new era were the trilobites, arthropods with jointed legs and gleaming exoskeletons. They scuttled along the bottom, their segmented bodies flexible yet armored, their compound eyes glittering like tiny mosaics. Trilobites ranged from the size of a thumbnail to nearly a foot long, feeding on detritus or smaller creatures, sometimes even on one another. They were explorers, burrowers, survivors, and their fossils now lie scattered across every continent, silent proof of their once global success. Sharing the seas with them was Anomalocaris, one of Earth's first apex predators. Its body rippled as it swam, propelled by undulating fins along its sides. Two grasping appendages extended from its head, ending in barbed hooks for snaring prey, and its circular mouth, ringed with overlapping plates, could crush anything unfortunate enough to drift too close. In a world newly filled with nervous systems and motion, Anomalocaris ruled. Not every creature was fierce. Some were simply strange. Hallucigenia, a tiny worm-like animal bristling with spines, looked like something drawn from a dream. For decades scientists couldn't tell which end was up. Opabinia carried 5 eyes and a long flexible proboscis ending in a claw, perfect for plucking food from the seafloor. Wiwaxia glided slowly across the mud, its back covered in scales and blade-like spines for protection. Each species was a new experiment, and most would never be repeated. Why the surge happened when it did remains one of science's most captivating questions. Some point to rising oxygen levels, allowing larger bodies and faster metabolisms. Others suggest ecological pressure, predation sparking an evolutionary arms race. Still others look to genetics, the emergence of regulatory toolkit genes that let evolution reshuffle the same basic parts into infinite forms. Whatever the cause, the effect was clear: life's creativity had been unleashed. The fossil record of the Cambrian captures this moment in exquisite detail. In places like Canada's Burgess Shale, China's Xinjiang beds, and Greenland's Sirius Posset, delicate impressions of creatures have survived in stone for 500 million years, muscles, eyes, even traces of soft tissue. They reveal an ecosystem already complex: predators and prey, scavengers and filter feeders, each dependent on the other in intricate loops of energy. For the first time, behavior itself became evolution's canvas. How an animal moved, how it sensed danger, how it hid or attacked, these choices mattered as much as anatomy. Nervous systems became more sophisticated. Muscles coordinated. Eyes transmitted information to primitive brains, which made split-second decisions that meant the difference between survival and extinction. With eyes came awareness, perhaps not thought as we know it, but a flicker of perception. Light could now be turned into knowledge: something is there. Predators learned to spot prey at a distance, prey learned to see the predator coming. The silent ocean filled with interaction. The evolution of sight was among the Cambrians' most profound changes. At first it was little more than a patch of light-sensitive pigment distinguishing day from night. Then pits formed, creating direction. Eventually, those pits deepened and curved, focusing light through primitive lenses. In that moment, the world gained edges, shapes, and movement. Arthropods such as trilobites developed compound eyes, arrays of tiny lenses that offered a panoramic mosaic view, perfect for detecting motion. Other animals evolved camera-type eyes with a single lens projecting an image onto a light-sensitive surface. Every design came with its advantages, and evolution explored them all. Vision changed everything around it. Once creatures could see, the environment itself began to respond. Prey hid in burrows or camouflaged against rock. Predators grew faster, sleeker, more coordinated. Shells thickened, armor hardened. The seafloor turned into a tapestry of pursuit and evasion. Even animals without eyes were affected. They dug deeper, lived nocturnally, or developed toxins for defense. The mere existence of vision reshaped the evolutionary landscape. Seeing meant planning, planning meant competition, competition meant innovation. Over time, eyes and movement co-evolved with nervous systems capable of processing complex information. Signals from sensors had to coordinate with muscles. Reactions became smoother, more efficient. The earliest brains emerged, tiny knots of nerve tissue capable of pattern recognition. They didn't think, not yet, but they responded, and that response drove survival. This interplay of senses and motion set the stage for intelligence as we understand it. Each new feedback loop rewarded awareness. Each success pushed evolution to refine perception, coordination, and behavior. The oceans, once a realm of drifting cells, had become a theater of strategy. Meanwhile, the physical world was also changing. Calcium carbonate secreted by countless tiny creatures began to accumulate, forming reefs. These early reefs, built by sponges and other simple animals, offered shelter and complexity, niches within niches. Where once the seafloor had been smooth, it now bristled with towers and caverns of living architecture. Life was not only adapting to its surroundings, it was creating them. Beneath these reefs, worms tunneled, churning sediment and releasing nutrients back into circulation. This process, bioturbation, was another quiet revolution, transforming the chemistry of the seabed and paving the way for future ecosystems. Small actions, repeated billions of times, remade the planet as surely as any asteroid strike. Open water ecosystems developed alongside these benthic ones. In the mid-water layers, animals learned not merely to drift but to swim. Streamlined shapes, muscles, and fins allowed them to chase food or flee predators. Some evolved armor for protection, others became transparent to vanish in plain sight. Every adaptation was an answer to a new question life itself had posed. The Cambrian seas also introduced the earliest known reproductive strategies beyond simple cell division. Some species released clouds of eggs and sperm into the water, others kept embryos safe inside until they could swim on their own. Each method shaped population dynamics and evolutionary speed. Reproduction had become more than replication, it had become a game of chances and strategies. All of this unfolded entirely underwater. The land above remained silent and bare, rock, sand, and wind. No green, no movement, only weather and stone. For hundreds of millions of years, the oceans would remain life's sole domain. Yet beneath their shimmering surfaces, the groundwork for the future was being laid. Because once the seas filled with swimmers and crawlers, something unexpected began to take root, literally. The ancestors of plants, simple photosynthetic organisms that had always hugged the water's edge, started adapting to shallow coastal environments. They clung to damp rock, surviving brief moments of dryness between tides. Step by step, they were preparing to leave the ocean behind. That story, though, belongs to another age. For now, picture the Cambrian Earth as a blue planet blazing with life. Sunlight filters through clear water onto gardens of coral-like sponges and carpets of algae. Trilobites crawl over rippled sand, worms weave tunnels beneath them. Predators glide overhead, their eyes scanning for movement. Everywhere, something is eating, growing, reproducing, dying. The rules of evolution, variation, competition, selection, are running at full speed. It's tempting to think of this as the beginning of life, but it was merely a new chapter in an ancient saga. All the complexity that dazzles us now, the forests, the birds, the languages, grew from the lessons learned in these seas. Here, in light filtered through water, awareness took its first shape. Here, the planet's long silence ended. When the Cambrian curtain finally began to close, the seas did not quiet. They only grew richer. Evolution had found its stride, and now it would not rest. The survivors of that explosive age, those that could adapt to the new arms race of hunter and hunted, would give rise to worlds beyond imagination. By the dawn of the Ordovician period, roughly 485 million years ago, the stage was set for an encore grander than the first. The ocean swelled with oxygen and nutrients, and continents slowly drifted apart, carving new shorelines and spawning warm, shallow seas. These calm, sunlit basins became nurseries for life. Coral-like animals called tabulate and rugose corals built reefs that stretched for miles. Brachiopods, creatures that looked a little like clams but weren't, covered the sea floor in astonishing numbers. Sponges, bryozoans, and mollusks joined them, weaving dense communities of filter feeders. Above them, new swimmers explored the open water. Slender nautiloids, with long conical shells and tentacled heads, glided like silent submarines through the blue. Each generation refined its armor, its senses, its speed. The Ordovician sea shimmered with color and motion, a ballet of shells and soft tissue. For the first time, ecosystems spanned every level, from microscopic plankton to giant predators, from grazers to scavengers. Food chains lengthened, energy flowed upward and back again. It was the planet's first truly interconnected web of life. And then, once more, Earth reminded its children that nothing lasts forever. As continents drifted toward the South Pole, glaciers formed, locking water into ice. Sea levels fell, temperatures plummeted, and habitats vanished. Nearly 85% of marine species perished in what became one of the first mass extinctions in history. Coral reefs crumbled, plankton populations collapsed, and the great nautiloids lost their hunting grounds. But extinction is never the end, it is change wearing its heaviest mask. When the ice melted and the seas returned, the survivors found a world cleared for innovation. New life surged again. Among it were small, jawless fish, the earliest vertebrates, slipping through the water with cartilage skeletons and rows of gill openings. They were awkward swimmers but revolutionary in design, bodies built around internal scaffolds instead of shells. Inside them lay the blueprint for every fish, reptile, bird, and mammal to come. These primitive fish evolved protective armor plates, heavy yet effective, giving rise to the ostracoderms. From them would eventually come something astonishing, creatures with jaws. But for now, they simply glided through the Ordovician dusk, silent witnesses to survival. As the Silurian period dawned around 443 million years ago, Earth's climate steadied. The seas grew warm again, reefs re-emerged like scars healing into beauty. In this calmer age, evolution turned its gaze toward refinement. Fish diversified, some developing paired fins for better control, others experimenting with light, flexible scales. Predators grew swifter, prey more elusive. Corals and sponges continued their architectural work, stacking calcium carbonate towers that sheltered endless forms of smaller life. Sea scorpions, or eurypterids, prowled these waters, some reaching more than 2 meters long, their paddle-shaped limbs propelling them like oars. They were among the planet's first true hunters capable of leaving the sea entirely for brief moments, scuttling onto damp sand to pursue prey or escape rivals. Above the tide line, something remarkable was happening. The once barren land began to show hints of green. Tiny photosynthetic pioneers, descendants of algae, had found ways to cling to moist rock near the shore. They were simple, no roots, no stems, just filaments absorbing sunlight and dew. But their presence changed everything. By anchoring themselves to stone, they slowed erosion. By photosynthesizing, they released oxygen directly into the air. And when they died, they left thin layers of organic matter that nourished the soil for those who would follow. Soon after came the first moss-like plants, spreading in low carpets along riverbanks. They could not yet stand tall or travel far from water, but they had taken the most daring step imaginable. Life had touched land. Where plants went, animals were quick to follow. Millipede-like detritivores and primitive scorpions crept ashore, feeding on decaying plant film. They were the first to breathe the alien air, their bodies armored against desiccation. Every inch of progress was a gamble, every breath a test, but each success opened a new frontier. Meanwhile, in the oceans, evolution prepared its next marvel, jaws. Up to this point, most fish could only suck or filter food. Then, through a transformation of gill arches, a few species evolved hinged, biting mouths. It was as if nature had suddenly discovered tools. Jawed fish could grasp, tear, and chew, they could become both predators and efficient grazers. This innovation birthed the placoderms, heavily armored fish that dominated seas and rivers alike. Among them were giants like Dunkleistus, a predator the length of a bus, its jaw plates acting as self-sharpening blades capable of slicing through armor. For 20 million years these titans ruled, until changing environments and competition thinned their line. But the concept of jaws would never vanish again. It was one of evolution's most powerful inventions. By the time the Devonian period began, around 419 million years ago, fish had conquered nearly every aquatic niche. Sharks emerged, sleek and efficient, lobe-finned fish developed muscular fins supported by bone, precursors to limbs. Coral reefs grew larger than ever before, sprawling ecosystems buzzing with color and motion. So much life filled the seas that scientists later called this time the Age of Fish. Yet under the surface of those same waters, a quiet revolution was brewing. Some lobe-finned fish began to linger in shallow, oxygen-poor lagoons. To survive, they evolved primitive lungs, extensions of the gut that could gulp air. Fins grew stronger, capable of pushing through thick mud or supporting weight for brief crawls between pools. Every adaptation whispered of something unprecedented, the first steps toward land vertebrates. At the edges of swamps and deltas, the boundaries between sea and shore blurred. Tidal flats shimmered under a warm sun, dotted with the first true plants rising upright, early ferns and club mosses, thin and fragile but taller than anything before them. Their roots held soil in place, their leaves released moisture, creating humid microclimates where insects thrived. The Devonian landscape would still look alien to modern eyes. There were no flowering plants, no birds, no mammals, only green stems, drifting spores, and the buzz of primitive arthropods. But the groundwork of terrestrial ecosystems was being laid grain by grain, spore by spore. Back in the seas, change never slowed. Ammonites, coiled shell relatives of nautiloids, spiraled into new shapes. Early sharks refined their sleek silhouettes, rays and other cartilaginous species began to appear. Meanwhile, coral reefs reached their zenith, towering underwater citadels that rivaled any modern reef in complexity. These structures teemed with life, sponges filtering water, crinoids waving feathery arms, fish weaving through caverns of living limestone. Yet Earth's balance is delicate, and even beauty can collapse under its own success. Toward the end of the Devonian, shifts in climate and sea level triggered another wave of extinctions. Reefs died back, and many armored fish disappeared forever. But just as before, survival carried seeds of invention. The descendants of those air-breathing lobe fins were growing ever more capable of movement on land. Their fins contained sturdy bones homologous to the humerus, radius, and ulna in our own arms. In shallows where oxygen was scarce and predators crowded, a strong fin could mean escape. Each step onto damp mud was the rehearsal for something monumental, the rise of amphibians, and eventually, all terrestrial vertebrates. The Devonian closed with the first forests spreading across continents. Trunks thickened, leaves broadened, roots tunneled deep, breaking rock into soil. The atmosphere filled with oxygen richer than it had ever known. The planet's colors changed, from gray and blue to green and gold. Life had finally seized two worlds, sea and land. The silence that had once ruled the continents was broken by the rustle of leaves, the hum of insects, the faint splash of creatures testing new gravity under an open sky. Earth's symphony had found a new movement, one played not only in waves but in wind. And somewhere, in the still pools left behind by receding tides, the ancestors of all land animals lifted themselves up, drew their first uncertain breaths of air, and began the long walk toward everything that would one day call itself human. The Devonian world faded into memory, and a new age dawned, an age of air thick with oxygen and forests so vast they swallowed continents. The year was somewhere around 359 million years ago, though time had long since lost meaning to anything but stone. The ocean still teemed with life, but for the first time, the land had grown louder than the sea. This was the Carboniferous period, named for what it left behind, immense beds of coal, the compressed ghosts of forests that once stretched from horizon to horizon. Every breath you take carries a whisper of that ancient air, oxygen levels so high they could have fueled flames to the clouds and allowed creatures to grow larger than ever again. Imagine walking through one of those forests. The air would feel heavy, humid, almost alive in your lungs. Towering trees, lepidodendron, sigillaria, calamites, rose like green skyscrapers, their trunks patterned with scales, their roots sprawling into swamps. There were no flowers yet, no grasses, only ferns, horsetails, and towering club mosses, their fronds unfurling in the dim light filtered through thick canopies. The scent would be rich with decay and damp soil. Everywhere, life thrived in abundance. At your feet, the ground squelched, a tangle of roots, fungi, and leaf litter. From the shadows scuttled centipedes as long as your arm, and beetles the size of birds. Above, the air shimmered with wings, dragonflies with 2-foot spans, their gossamer bodies gliding like living aircraft. These were the Meganeura, the largest insects to ever fly, their size made possible by oxygen-rich air and the absence of birds to hunt them. The forests were not quiet. Chirps, clicks, and croaks echoed through the swampy gloom. The first amphibians, descendants of the Devonian fish that had crawled from the shallows, now reigned on land and in water alike. Some looked like enormous salamanders, others bore the flattened skulls of crocodiles. They breathed through lungs and skin, their eggs still tied to water, their young beginning life as tadpoles before growing legs. These early amphibians, like Ichthyostiga and Acanthostiga, were pioneers of two worlds. Their bodies spoke of compromise, limbs strong enough to support them on land, but tails and gills still clinging to the past. Every movement across the swampy banks was a rehearsal for something grander. Amphibians ruled the freshwater rivers, lakes, and floodplains, feeding on insects and small fish. But as their numbers grew, so did their challenges. Dry seasons turned ponds to dust, eggs laid on open ground perished without moisture. The planet had offered new ground, but it came with new rules. To conquer land completely, life would need another innovation, one that would free it forever from the pull of the water. Before that leap, though, the Carboniferous reached its height. For nearly 60 million years, vast wetlands blanketed what would one day become North America, Europe, and Asia. Rivers wound through fern jungles, rains fell with tropical regularity. The continents themselves were slowly drifting toward one another, gathering into a single colossal landmass called Pangaea. Its assembly would shape everything that followed: climate, ocean currents, and evolution itself. Deep in those forests, something remarkable was happening underground. Plants, in their endless race towards sunlight, had invented lignin, a complex polymer that made wood strong and rigid. But in that era, no fungi or bacteria could yet digest lignin efficiently. When trees died, they didn't rot completely, they fell, sank into oxygen-poor swamps, and accumulated in layers. Over millions of years, pressure turned those layers into coal, the fossilized memory of an age that breathed too well. The air's richness came at a cost. With oxygen levels near 35%, almost double today's, wildfires swept across dry forests like living storms. A single spark could ignite a blaze that burned for weeks. Yet life endured, even flourished, amid the flames. Wherever something burned, something new grew in its place. Beneath the canopy, evolution experimented once again. Some amphibians developed thicker skins and more efficient lungs. A few species began laying eggs encased in protective membranes, allowing embryos to survive away from water. That innovation would change the course of life forever. The amniotic egg, complete with shell, fluid, and built-in nourishment, freed reproduction from ponds and streams. The creatures that laid them were the first reptiles, small at first and easily overlooked, but destined to dominate for hundreds of millions of years. Each egg was a portable ocean, a miniature world carrying the memory of water within it. With it, life had learned to bring the sea to land. Reptiles spread quickly through the forests. They were leaner and drier than amphibians, their scales sealing in moisture. Some hunted insects, others scavenged among roots and fallen trunks. They walked with a confidence amphibians never could, their legs pushing beneath their bodies instead of sprawling to the sides. For the first time, vertebrates truly belonged to the land. As reptiles diversified, the Carboniferous world began to change again. The same processes that had built its lush jungles now conspired to end them. Volcanic eruptions and shifting continents altered the global climate, drawing the planet into a cooler, drier state. Swamps retreated, forests thinned. The once endless wetlands gave way to open plains and seasonal droughts. Amphibians, tied to water for breeding, suffered first. Their eggs dried, their skin cracked. But reptiles thrived, carrying their portable nurseries wherever they roamed. By sheer resilience, they became the heirs of the land. During this transition, Earth's face transformed once again. The continents moved closer together, fusing into the near supercontinent Euramerica, a prelude to Pangaea. Mountain ranges rose from colliding crust, inland seas drained. The humid swamps that had defined the Carboniferous slowly faded, replaced by drier forests and vast floodplains. Yet even as the forests waned, their influence endured. The oxygen-rich air they left behind shaped everything that followed. Gigantic arthropods continued to roam the land. Arthropleura, a millipede more than 2 meters long, crawled through fallen leaves like a living train. Giant dragonflies still drifted through the canopy, their wings glinting in the sunlight like glass. And in the rivers, massive amphibians lingered, ancient reminders of the world before eggs learned to travel. At night, the forests glowed faintly with the reflections of moonlight on damp trunks and still water. The sounds of insects filled the air in rhythmic waves, and the chorus of frogs echoed through the darkness. It was a living world, exuberant and self-sustaining, unaware that its own success was changing the climate around it. As the Carboniferous gave way to the Permian period, the air began to dry. Ice reappeared at the poles, and global sea levels fell. The once vast tropical belt narrowed, leaving deserts where rainforests had once stood. The age of coal was ending, and a new world, harsher, drier, more selective, was beginning to emerge. But before we step into that harsher land, pause for a moment and imagine the stillness of those Carboniferous jungles. The dripping of condensation from tree ferns. The hiss of insects brushing their wings. The damp heat that wrapped every living thing like breath. Those forests were Earth's lungs, an age where the planet inhaled deeply and filled itself with life. Everything that would follow, the reptiles, the dinosaurs, the mammals, the humans, owed their existence to the air first made there. The Carboniferous was more than an age of coal and fern. It was the age when Earth learned to breathe, and in that breath lay the promise of all future life. The Carboniferous rainforests faded, their green cathedrals collapsing under the slow weight of drought and time. The air cooled, the swamps dried, and rivers that had once wound through endless jungles shrank into dusty channels. The earth was changing again, subtly at first, then with the unstoppable patience only geology knows. This was the dawn of the Permian period, beginning roughly 299 million years ago. It opened with silence, fewer insects buzzing, fewer frogs croaking, the hush of forests retreating. But in that silence, a new empire was gathering its strength, the empire of reptiles. Freed from the need to lay their eggs in water, they spread into every corner of the continent. Their scaly skin conserved moisture, their lungs drew deep from the thinning air. They were leaner, more self-contained, and better suited to the drying climate than their amphibian cousins. Each sunrise saw them pushing farther from the rivers, their shadows stretching across lands no creature had yet claimed. The world itself had grown stranger. Continents that had once floated apart were now colliding, crushing mountains skyward. Oceans narrowed into inland seas, and a single supercontinent, Pangaea, took shape, an enormous mass of rock and desert that stretched from pole to pole. It was surrounded by a single global ocean called Panthalassa, vast and restless. From space, had anyone been watching, Earth would have looked both familiar and alien, half land, half sea, wearing a face we will never see again. Pangaea's heart was arid and brutal. Seasonal rains barely touched its center, sandstorms swept across endless plains. But along the coasts and deltas, life flourished. Forests of conifers and seed ferns took root, and rivers carved green ribbons through the red rock. Here reptiles evolved into shapes that would echo through all of deep time. Among the earliest were the pelycosaurs, sail-backed reptiles like Dimetrodon. Despite its fearsome appearance, Dimetrodon wasn't a dinosaur. It lived almost 60 million years before the first dinosaur ever drew breath. Its tall sail of bone spines, stretched with skin, may have helped regulate temperature or attract mates. With serrated teeth and a powerful bite, it ruled the river valleys as one of the first large land predators. From the pelycosaurs came a lineage more advanced and more familiar to us than we might imagine, the therapsids. Sometimes called mammal-like reptiles, they were warm-blooded pioneers, experimenting with features that would one day define our own kind, differentiated teeth, upright legs, faster metabolisms, even hints of fur. Their eyes faced forward, their ribs moved with steady breath. They hunted, grazed, raised young, and filled the continents with new possibilities. The Permian was a time of innovation wrapped in hardship. The climate swung wildly, intense droughts, then monsoons, then frost. Pangaea's vast interior baked in summer and froze in winter, forcing life to adapt or vanish. Those who survived became tougher, more efficient, more cunning. Reptiles spread outward, colonizing every niche. Some returned to the sea, evolving flippers and streamlined bodies, others became swift desert hunters. Insects, too, diversified. Cockroaches, beetles, and the first true flies appeared, mastering air and land alike. On the coasts, coral reefs rebuilt themselves after the devastations of earlier ages, only to fall again when the sea chemistry shifted. Life was learning flexibility, the most powerful survival tool of all. Forests of towering conifers and ginkgos rose in the cooler climates, while vast stretches of desert sand dunes covered what is now North Africa and the American Southwest. The air smelled of resin and dust, not of wet decay. It was a planet midway through reinvention, half the lush world of the Carboniferous, half the dry, open earth of later ages. Amid all this transformation, the therapsids thrived. There were herbivores like Dicynodon, squat and tusked, grazing in herds beneath the sun. There were predators like Gorgonops, sleek and muscular, with saber-shaped canines and the agility of a cat. They were intelligent by reptilian standards, alert, quick, adaptable. For tens of millions of years, they ruled the continents unchallenged. But deep beneath their feet, something was stirring. Tectonic forces twisted the crust, volcanoes built pressure that had nowhere to go. The stage was being set for catastrophe. Toward the end of the Permian, roughly 252 million years ago, the Earth convulsed. In what is now Siberia, fissures tore open in the land, unleashing the Siberian traps, one of the greatest volcanic events in history. For nearly 1 million years, rivers of lava poured out, covering millions of square kilometers. Ash and toxic gases filled the air. Sulfur clouds dimmed the sun, plunging the world into darkness. At first, temperatures dropped. Then, as carbon dioxide flooded the atmosphere, they soared. Oceans warmed and lost oxygen, methane released from the seafloor, amplifying the chaos. Rain turned acidic. Forests withered, rivers carried poison instead of life. The sky itself became a weapon. This was not a single disaster but a chain reaction of them, a planet unraveling under its own chemistry. Coral reefs collapsed. Shellfish, trilobites, and countless marine species suffocated in stagnant seas. On land, forests burned, and food webs crumbled. Predators starved when prey vanished, scavengers found only ash. When the smoke finally cleared, more than 90% of marine species and 70% of land species were gone. It was the worst mass extinction Earth has ever known, the Great Dying. Imagine standing there, if you could survive it, a horizon dim with ash, rivers black with soot, silence heavy where once the forests sang. The smell of sulfur and char hung over continents. Even the insects, normally invincible, nearly vanished. It was as though the planet had pressed a reset button, erasing the intricate world it had built over hundreds of millions of years. And yet, life endured. A few lineages of therapsids clung to survival in shaded valleys and along the edges of dying rivers. Some small reptiles persisted, burrowing underground or sheltering in crevices. In the oceans, tiny plankton rebuilt the base of the food chain grain by grain. Slowly, painfully, the earth began to heal. Volcanoes finally stilled, rain returned, new soil formed over old lava. Where barren plains had stretched, mosses and ferns crept back first. Within a few million years, an instant in geologic time, forests began to grow again, and ecosystems reorganized themselves around the survivors. From among the humbled remnants of the Permian world, a new caste of creatures emerged, tougher, faster, more efficient. Among them were the archosaurs, a group of reptiles that would one day give rise to crocodiles, pterosaurs, and the dinosaurs themselves. From the ashes of extinction, the age of reptiles was about to begin. The Permian had ended in fire, but from that fire came the spark of the next great story. Life, bruised but unbroken, stood ready to begin again. The earth had changed its face many times before, and it would again. It always does. When the Permian fires finally burned themselves out, the earth was quiet again. Too quiet. The forests were gone, the reefs were gone, even the air seemed thinner, as though the planet itself were catching its breath. Yet beneath the stillness, the same old rhythm persisted, the rhythm that had carried life through every disaster before. One cell divides, another feeds, another hides. In that persistence lay the promise of recovery. And recover it did. Slowly, carefully, the world began to stitch itself back together. Rain fell again, washing the poison from the skies. Oceans refilled with oxygen, and new microbial mats carpeted the shallows. From scattered survivors, the web of life began to weave itself anew. This was the dawn of the Triassic period, around 252 million years ago, the first chapter of the Mesozoic era, the age of reptiles. For millions of years, the planet had been nearly empty, a blank slate waiting to be redrawn. Evolution, as always, rose to the challenge. At first, the land was sparsely populated. The survivors of the Great Dying were small, cautious creatures, insects scurrying through ferns, amphibians lurking in rivers, and a few hardy reptiles creeping across cracked soil. The dominant therapsids, those mammal-like reptiles that had ruled the Permian, were reduced to shadows of their former selves. But the emptiness they left behind was opportunity, and evolution abhors a vacuum. Among the new survivors were archosaurs, a lineage of reptiles that adapted brilliantly to the dry, unpredictable Triassic world. They came in many shapes, some crocodile-like, some lightly built runners, others with hints of the grandeur yet to come. Strong legs, efficient lungs, and durable eggs gave them an edge in the shifting climate. From these archosaurs, two dynasties would rise, one that would dominate the air and another that would dominate everything else. In the seas, too, recovery was underway. Coral reefs reappeared, and the first marine reptiles took to the water. Long-bodied ichthyosaurs evolved from land reptiles, their limbs reshaped into fins, their bodies streamlined like dolphins. They hunted fish and squid in the open ocean, diving deep and giving birth to live young in the waves. Soon after came the plesiosaurs, with long necks and paddle-like limbs, gliding gracefully through shallow seas. The ocean, once again, was alive. On land, forests of conifers and cycads began to spread. Seed-bearing plants, gymnosperms, thrived where ferns had once ruled, covering Pangaea in a patchwork of green. Amid this slow renewal, the first small mammals appeared, descendants of the surviving therapsids. They were no larger than mice, scurrying in the shadows, hunting insects by night and hiding by day from the rising reptilian rulers. Tiny, warm-blooded, and furred, they were fragile but persistent, life's quiet insurance policy against the giants to come. Because above them, another story was taking shape. In the mid-Triassic heat, a group of bipedal archosaurs began to evolve longer hind legs, lighter bodies, and tails that acted as counterweights. They stood upright, balancing their weight to move with astonishing speed and agility. These were the earliest dinosaurs. At first, they were small, no taller than a person, with slender limbs and quick reflexes. They darted through forests, chasing insects and small prey, or scavenging carcasses left behind by larger reptiles. But their advantages, efficient lungs, strong legs, and eggs that could survive in dry climates, soon turned them from survivors into conquerors. Within a few million years, dinosaurs had spread across every continent. The Triassic world was harsh, blistering days, cold nights, erratic rainfall. But it was also dynamic, full of opportunity for creatures that could adapt. While mammals hid and amphibians clung to dwindling wetlands, dinosaurs became masters of the land. Some evolved long necks for reaching high vegetation, others grew sharp teeth for tearing flesh. Predators and prey began their eternal dance once again. And then, about 230 million years ago, the first pterosaurs took to the skies. They weren't birds, not yet, but winged reptiles whose arms had transformed into aerodynamic marvels. Their wings stretched on elongated fourth fingers, membranes supported by muscle and bone. Lightweight skeletons and powerful chests made them natural flyers. With the air now clear and full of insects, the sky had opened its doors. For the first time, vertebrates ruled all three realms, land, sea, and air. As the Triassic wore on, the world's ecology matured. Rivers wound through conifer forests, deserts gave way to savannas filled with cycads and ferns. Carnivorous dinosaurs like Heterosaurus and Coelophysis prowled the floodplains, hunting in packs or alone. Their prey included early herbivores such as Plateosaurus, one of the first large plant-eating dinosaurs, whose long neck and heavy tail hinted at the giants to come. But the Triassic would not end gently. Once again, Earth reminded its creations of impermanence. Volcanic activity surged as Pangaea's crust began to fracture. Immense lava flows erupted along what is now the Atlantic coast, releasing carbon dioxide and triggering global warming. As temperatures spiked, ecosystems collapsed. Up to 75% of species vanished, clearing the stage once more. The Triassic gave way to the Jurassic period, and in that void, the dinosaurs rose fully to power. By 201 million years ago, the world was greener, warmer, and wetter again. Rainforests spread across the tropics, ferns and cycads flourished. Pangaea was splitting apart into new continents, creating coastlines, inland seas, and fresh habitats. The survivors of the extinction radiated outward to fill every niche, and the dinosaurs led the charge. The Jurassic Earth was a paradise for giants. Among the first to tower over the land were the sauropods, long-necked, long-tailed herbivores that reached heights and weights never before seen. Diplodocus, Brachiosaurus, and Apatosaurus moved in herds through lush valleys, stripping trees bare with each slow sweep of their necks. Their size was protection, few predators dared challenge them. Every step they took shook the earth, yet their movements were deliberate and calm, living mountains grazing on a green world. In their shadow moved the hunters. Slender, quick-footed predators like Allosaurus stalked the plains, relying on intelligence and cooperation. Some hunted alone, others may have worked in groups, driving prey into traps or ambushes. The air around them shimmered with heat and life, buzzing with insects and filled with the calls of reptiles echoing through forest canopies. Above it all, the skies belonged to the pterosaurs. Their forms had diversified, some small as sparrows, others with wingspans of 20 feet. They glided along coastal cliffs, dove for fish, or hunted over inland lakes. Their bones were thin as paper yet strong as steel, built for endurance rather than brute strength. They were the first to master flight, and they would hold the skies for more than 150 million years. Meanwhile, beneath the branches of cycads and conifers, a quieter story continued. The small, nocturnal mammals, those furry survivors from the shadows, persisted through the age of giants. They hunted insects, climbed trees, and cared for their young in burrows and hollows. Their warm blood and sharp senses made them nimble in the darkness, safe from the reptilian lords who ruled by day. Evolution was patient with them, storing its cleverest ideas in their tiny bones until the world was ready. The Jurassic world was lush beyond imagination. Rainfall fed wide rivers, volcanic soil nourished endless forests. Huge ferns, horsetails, and towering conifers covered the land in a tapestry of green. Ammonites, spiraled mollusks, drifted through the seas, while ichthyosaurs and plesiosaurs patrolled the depths. Everywhere was motion, life, and noise. It's easy to see this era as stable, a long golden age, but the truth is more delicate. Even in its abundance, the Earth never stopped changing. Volcanoes reshaped coastlines, continents drifted farther apart, and new ecosystems evolved to match each twist in climate. What we call ages are simply pauses between upheavals. Still, for more than 50 million years, the dinosaurs held dominion unchallenged. They filled every shape evolution could imagine: massive plant eaters, swift hunters, armored defenders, and horned guardians. Their reign seemed eternal. But as we've learned, no empire, no matter how vast, lasts forever. For now, though, in the warmth of the Jurassic sun, life had achieved a kind of harmony. The skies were alive with wings, the seas with swimmers, the land with titans. It was a world of abundance and balance, built upon the ashes of the one that came before. And somewhere in the undergrowth, a small mammal stirred in its burrow, blinking against the dawn. It didn't know it was living in the shadow of giants, or that one day its descendants would inherit the earth. It simply listened, to the rustle of leaves, the distant thunder of footsteps, and the whispers of a planet always ready to begin again. The Jurassic sun shone on a world at peace with its chaos. Forests swayed, seas glittered, and creatures of impossible shape filled every horizon. Yet, as always, change was already on the move. The slow turning of continents, the quiet shifting of air and sea, these ancient forces never truly sleep. By around 145 million years ago, the Jurassic gave way to the Cretaceous period, and Earth was once again remade. The supercontinent Pangaea had finally split apart. New oceans opened between drifting lands, mountain chains rose where plates collided. The planet grew warmer, wetter, and more complex. Coastlines stretched for thousands of miles, shallow seas flooded the interiors of continents, and the air hummed with the promise of life evolving in 1,000 directions at once. It was the age of giants perfected, yet it was also the age of quiet revolutions. The great sauropods still ruled the plains, their necks sweeping through canopies of ancient conifers and cycads. Species like Argentinosaurus grew to over 30 meters long, the heaviest land animals to ever live. Each heartbeat pumped hundreds of gallons of blood through bodies the size of cathedrals. Their herds moved like slow weather fronts, reshaping the landscape as they fed. Where giants walked, predators followed. The Jurassic's Allosaurus gave way to new rulers, the Tyrannosaurs, the Abelisaurs, and a host of fierce hunters evolved to match their prey. They grew larger, faster, more intelligent, their senses honed for pursuit. At the top of this food chain stood one name the world would never forget: Tyrannosaurus rex. With jaws capable of crushing bone and eyes that faced forward for depth and precision, T-Rex was more than just strength, it was strategy. It could smell prey miles away, sense motion with near-perfect accuracy, and its brain, though small, was specialized for focus and coordination. It wasn't mindless fury, it was evolution distilled into power. But the Cretaceous world was far more than monsters and teeth. A subtler transformation was underway, one that would forever change the color, scent, and rhythm of the planet. In the shadows of conifers, a new kind of plant appeared. At first, it looked unremarkable, small shrubs with delicate petals and enclosed seeds. But these newcomers had a secret weapon: partnership. They lured insects with nectar and pollen, turning reproduction into collaboration. These were the flowering plants, or angiosperms. With them came a sensory revolution. For the first time, Earth bloomed in color. Petals painted the land in crimson, violet, and gold, while scents drifted on warm breezes, calling bees, beetles, and butterflies into service. Insects evolved alongside them, perfecting the art of pollination. Each color, each fragrance, was a signal, an ancient language of attraction and exchange. As the plants diversified, so did their partners. Beetles buzzed between petals, carrying pollen. Ants marched through the roots and stems, defending their hosts in exchange for food. And among the trees, new life was stirring in the branches. Feathers, which had first appeared among small predatory dinosaurs for insulation or display, began to take on a new purpose: flight. The first true birds took to the air, their bones hollow and light, their forelimbs transformed into wings. They were not yet masters of the skies; their ancestors, the pterosaurs, still ruled that realm, but they were learning fast. Archaeopteryx, with its feathered wings and reptilian tail, was among the earliest of them, straddling two worlds, the old and the new. The air above the forests now shimmered with movement, dragonflies, birds, and pterosaurs weaving among the trees, each pursuing its own invisible currents of wind and instinct. Below, mammals remained small, but quietly ingenious. They chewed, they nurtured, they cared for their young in ways their reptilian neighbors never could. Hidden among roots and ferns, they bided their time. The Cretaceous was a golden age of abundance. The seas teemed with life. Mosasaurs, massive, serpent-like predators, glided through warm inland waters, while plesiosaurs and ichthyosaurs patrolled the coasts. Ammonites drifted in spiral shells, their numbers beyond counting. On coral reefs, fish darted in dazzling colors, and giant clams filtered the tides. Every ecosystem, from the deepest trench to the highest branch, thrummed with vitality. Yet even in such beauty, the signs of imbalance were there. Volcanic activity increased. Sea levels rose and fell as the continents shifted and climates swung between extremes. The Earth's engine, ever restless, was preparing once again for change. Inland, forests grew dense with flowering plants and fast-spreading grasses. Herbivorous dinosaurs adapted, evolving beaks and complex teeth to grind the new vegetation. Among them were the hadrosaurs, or duck-billed dinosaurs, who grazed in herds and likely communicated through low, resonant calls that rolled across the plains. Others, like the ankylosaurs, armored themselves in plates of bone and swung tail clubs like maces against predators. The ceratopsians, crowned with horns and frills, became living fortresses, Triceratops chief among them. Everywhere, nature experimented with shape and strategy. Speed, armor, camouflage, communication, all evolved in an escalating spiral of survival. Predators grew smarter, prey more coordinated. For tens of millions of years, balance held. And then, in the quiet skies over a shallow sea near what is now Mexico, fate arrived from beyond the world. 66 million years ago, a piece of rock 6 miles wide crossed the void at 30,000 miles per hour. It struck the Yucatan Peninsula with the force of billions of nuclear bombs. The earth shook, the sea rose as a wall of fire and water. Shockwaves circled the globe. Forests ignited. The sky filled with molten dust that turned day to night. For months, perhaps years, sunlight barely reached the surface. Temperatures plunged, photosynthesis halted, and the food chains collapsed. In that darkness, the age of dinosaurs ended. 3/4 of all species vanished. The great reptiles of land, sea, and air were gone. But life did not die, it adapted, as it always had. The small mammals that had hidden in burrows and tunnels emerged to a changed world. They were survivors of instinct and endurance, feeding on seeds and insects while the giants fell around them. When the ash finally settled, the world was quiet again, but not empty. The stage was open once more, waiting for new players. From the silence after the fire came rebirth. Forests returned, green and strange. Birds, the last living dinosaurs, filled the air with their voices, the echoes of ancestors who once thundered on the ground. And from the mammals came curiosity, intelligence, and, eventually, a species that would look back on it all and give it names. The Cretaceous world was gone, but its whispers remain in stone and bone, in the curve of a bird's wing, in the bloom of a flower, in the memory of survival itself. The planet had turned a page once again, and though its story had lost its giants, it had gained its future. The age of dinosaurs was over. The age of change was not. When the dust of the great impact finally began to settle, the earth exhaled again. The skies cleared, sunlight returned, and the long silence of extinction slowly gave way to the rustle of new life. The planet had survived yet another ending. But what emerged from the ashes would look nothing like the world that came before. This was the beginning of the Cenozoic era, the age of mammals, around 66 million years ago. It began not with thunder, but with the faint scurrying of survivors beneath ferns and fallen trunks. Where titans had fallen, tiny, warm-blooded creatures crept into the open. They were small, quick, and clever, mammals who had waded through the reign of the dinosaurs, surviving on insects, roots, and patience. Now the stage belonged to them. The early Cenozoic world was scarred but fertile. Volcanoes still smoked where the asteroid had struck. Forests regrew across continents blackened by fire. The air, once choked with ash, now shimmered with sunlight. Rivers carried minerals into reborn seas, feeding plankton and corals that would rebuild entire ecosystems from microscopic beginnings. At first, the mammals were modest, shrew-like insect eaters, nocturnal and cautious. But in the absence of giants, opportunity spread like dawn. Some grew larger, others learned to climb, dig, or swim. Within a few million years, evolution was once again experimenting with shape and function at a dizzying pace. Out of this experimentation came the Paleocene, the first epoch of the Cenozoic. The planet was warm, blanketed in tropical forests from pole to pole. Crocodiles basked in Arctic swamps, and palm trees grew where snow would one day fall. Birds, the last surviving dinosaurs, filled the air, their wings painting the sky with life once more. Some, like the terror birds of South America, became apex predators in their own right, flightless, swift, and armed with hooked beaks capable of snapping bone. Meanwhile, mammals diversified into every niche the dinosaurs had left behind. Hoofed herbivores grazed on the new greenery, early primates leapt through branches, and carnivorous mammals hunted in the shadows. Each form was a new experiment, each generation refining what survival meant in a changed world. Then came the Eocene epoch, around 56 million years ago, and the Earth entered a time of warmth and abundance. Rainforests expanded, coral reefs flourished, oceans teemed with life. Whales evolved from land-dwelling ancestors, four-legged mammals that waded into shallow seas, adapted to hunting fish, and gradually surrendered their legs for flippers. The first true whales, like Basilosaurus, stretched nearly 20 meters long and moved through the water like living shadows. The ocean had found its giants again. On land, familiar families emerged. The ancestors of elephants, horses, bats, and even primates began to take recognizable form. Rodents scurried through undergrowth, early carnivores stalked them with quiet precision. The world, once emptied by disaster, was filling with motion and sound once more. In the trees, small, bright-eyed mammals clung to branches with grasping hands. Their forward-facing eyes gave them depth perception, the ability to judge distance and leap from limb to limb. They lived in tight social groups, nurturing their young and learning from one another. These were the first primates, and they carried within them a spark that would one day light the path toward thought. The Eocene Earth would have felt like paradise, lush, wet, vibrant. But nature never stops moving. Tectonic plates continued to drift, mountains rose, and oceans shifted. Around 34 million years ago, as the Oligocene epoch began, the planet began to cool. Forests retreated, grasslands expanded, polar ice reappeared. Animals that had once hidden in jungles now learned to run in open plains. Hoofed mammals diversified into grazers and browsers, horses, antelopes, and camels. Predators evolved speed and endurance to match them, early dogs and cats honing the chase. The balance of predator and prey shifted from ambush to pursuit. This was a new kind of world, open, fast, dynamic. In the oceans, whales perfected their art. Some developed baleen plates to filter plankton, others became hunters of seals and fish. Dolphins appeared, playful and intelligent, their clicks and songs echoing through the deep. Even here, in the water's silence, communication had become a survival tool. By the Miocene epoch, roughly 23 million years ago, the continents had taken on shapes we would almost recognize today. The Himalayas towered where India had collided with Asia, reshaping global weather. Africa drifted north, narrowing the gap with Europe and setting the stage for migrations that would one day include our ancestors. The air cooled further, savannas spread. Forests gave way to grasslands where herds of animals thundered across the horizon. Among them roamed familiar silhouettes, elephants with tusks, rhinos, giraffes, antelopes, and great cats. Birds of prey circled overhead. Everywhere, ecosystems pulsed with complexity and motion. Life had once again mastered its balance. And in the trees of Africa and Asia, the apes emerged. Descended from earlier primates, they had larger brains, flexible hands, and eyes filled with awareness. They learned to use tools, sticks to probe, stones to crack, gestures to communicate. Curiosity had found its voice. The apes spread across continents. Some took to the forests, others ventured into the open woodlands where grass met tree. They lived in groups, nurtured offspring, and began to form social bonds that reached beyond mere instinct. Cooperation, empathy, and planning, the earliest sparks of intelligence, were beginning to glow. Then came the Pliocene, about 5 million years ago, when the Earth's rhythms began to cool once more. Ice sheets crept down from the poles, reshaping coastlines and redirecting winds. In East Africa, shifting climates turned dense forests into patchy savannas. For some apes, this change was a challenge, but for others, it was an opportunity. Some began to spend more time on the ground. They stood upright to see above tall grass, freeing their hands to carry food or young. Their spines straightened, their feet flattened. They walked not on 4 limbs, but on 2. The first hominins, our earliest ancestors, had appeared. They were not yet human, but they were something new, creatures who could look to the horizon and move toward it. They fashioned simple tools from stone, hunted in groups, and learned to share what they found. Their brains grew larger, their curiosity deeper. The world had given rise to thinkers. As the Pleistocene epoch began, roughly 2.6 million years ago, the planet entered an age of ice and rhythm, cycles of freezing and thawing that sculpted continents anew. Glaciers advanced and retreated, carving valleys, creating lakes, and shaping the world we know today. Amid this cold beauty, new species emerged, creatures built for endurance. Mammoths and mastodons roamed the tundra, covered in woolly coats. Saber-toothed cats hunted bison and deer. Huge ground sloths lumbered through forests, and bears grew massive in the north. Human ancestors, Homo habilis, Homo erectus, and eventually Homo sapiens, spread across the continents. They mastered fire, crafted tools, and began to tell stories in the flicker of flame and shadow. Every step they took echoed the journey of life itself, from molecule to cell, from water to land, from survival to awareness. The Earth had not planned this outcome, it had simply allowed it. Each extinction, each rebirth, each quiet adaptation had paved the way for thought. And though the mammoths and saber-tooths would one day vanish, and though ice would give way again to warmth, something enduring had appeared on the planet's surface, something that could wonder why it was here. The Cenozoic was more than just the age of mammals. It was the age when the Earth learned to look back at itself through the eyes of its children. Every bird, every forest, every human heartbeat is still part of that story. The age of giants had ended long ago, but the age of awareness had just begun. The Ice Age was both a sculptor and a storyteller. For nearly 2.5 million years, glaciers carved mountains, widened valleys, and left fingerprints across every continent. They advanced and retreated in slow rhythm, grinding stone into soil, shaping rivers, and building the landscapes we walk on today. Beneath their frozen weight, the planet rested and remade itself. And through that long winter, one species of ape was learning how to endure. They were hunters and wanderers, their lives measured by firelight and footsteps. They tracked herds across frozen plains, followed rivers through forests, and built shelters from bone, hide, and hope. They carried tools sharper than instinct, and inside their skulls something extraordinary was unfolding, a mind not only capable of survival, but of imagination. This was Homo sapiens, our kind, emerging roughly 300,000 years ago in Africa. At first, we were just another branch in a family tree already thick with cousins, Homo erectus, Homo neanderthalensis, Homo floresiensis, and more. Each species carved its own path, adapted to its own home. But our ancestors had something subtle yet decisive, adaptability shaped by curiosity. They painted with ochre, carved bones into beads, and buried their dead with care. They learned to tell stories, perhaps by accident, sounds shaped into meaning around campfires. Stories that remembered the hunt, honored the fallen, and gave reason to the stars. In those stories lay the seeds of everything that would follow: art, myth, culture, civilization. By 100,000 years ago, our ancestors had begun to wander beyond Africa. They crossed deserts and mountains, followed shorelines, and spread into Europe, Asia, and eventually the islands of the Pacific. Some met their Neanderthal relatives and shared more than encounters, they shared genes, memories, and perhaps even dreams. By 40,000 years ago, humans had reached Australia, by 15,000, the Americas. Every continent but Antarctica now carried their footprints. Wherever they went, they left traces: caves painted with bison and mammoths, tools shaped from flint, and hearths blackened with smoke. They hunted in teams, crafted spears and arrows, and learned to read the movements of the sky. They observed seasons, stars, tides, and the rhythms of life. For the first time, the planet itself had a species aware of its patterns. But awareness brought power, and power brought change. When the last great ice age began to fade around 12,000 years ago, glaciers withdrew to the poles. Sea levels rose, carving new coastlines. Grasses spread across warming plains, and herds followed them. Humans, always observant, noticed that seeds dropped near their camp sprouted where they fell. From this small revelation grew the greatest transformation in our history. The agricultural revolution began quietly: grains in the Fertile Crescent, rice in East Asia, maize in the Americas. People began to settle, to build, to stay. Villages became towns, towns became cities. We domesticated animals, stored food, and shaped the land to our needs. The wild hunter's world gave way to one of harvests and hearths. Civilization rose on the banks of rivers, the Nile, the Tigris, the Indus, the Yellow River. We built temples, walls, and monuments that reached toward the gods we imagined from the stars. Writing emerged as a way to remember what the mind could no longer hold alone: laws, trade, stories. Metal followed stone, and cities glowed in the firelight of bronze and iron. The earth, which had once shaped us entirely, was now being shaped by us. We cut forests for fields, dammed rivers for crops, mined mountains for ore. We learned to bend elements into tools and weapons, to build ships that crossed seas, to measure time itself. The planet's surface began to bear the marks of intention. Empires rose and fell like tides. Knowledge flickered between them, growing brighter with each return. Mathematics, astronomy, philosophy, all born from curiosity and observation, became our new survival tools. Where once adaptation had been physical, now it was mental. We reshaped our environment not by evolving bodies, but by evolving ideas. Yet every tool came with a shadow. The same hands that built also burned. The same fire that cooked also conquered. Civilization expanded, and with it came competition, conflict, and consequence. Forests shrank, species vanished, the balance that had held for billions of years began to tilt. Still, even amid the noise of cities and machines, the ancient whispers never faded entirely. They linger in the wind, in the grain of wood, in the pulse beneath the ground. Every breath of air still carries atoms that once drifted through ancient seas. Every heartbeat still follows rhythms written long before names existed. In the last few thousand years, an instant in the planet's deep history, humans have done what no species before them dared: they began to reshape the entire world deliberately. We bridged oceans, climbed mountains, split atoms, and looked back at Earth from beyond its skies. We saw our home not as infinite, but fragile, a blue jewel in darkness. And in that vision, something both wondrous and humbling took root: awareness of responsibility. Because the story of Earth is not separate from us. It never was. We are its continuation, the echo of volcanoes and oceans, of molecules that once drifted in starlight. Every thought, every city, every song is a ripple in that unbroken chain. The ice ages have passed, but the world still shifts beneath us. Climate, once sculpted by stone and orbit, now responds to our choices. Forests fall or grow by our hand. Species live or vanish because of us. For the first time, the storyteller can alter the story as it's told. We stand now at a crossroads not of geology, but of intention. The planet will endure, it always has. The question is whether we will endure with it, and what kind of ancestors we will become to the future that follows. Look around you, the mountains, the oceans, the wind in the trees. All of it is older than memory, yet still alive, still becoming. The same chemistry that birthed the first cell still burns within your veins. You are made of oceans and starlight, of dust and time. The journey that began in molten rock and silent seas has led to this moment, to consciousness looking back upon its source. The story of Earth is not over, because you are part of it. Every act of kindness, every creation, every question asked in wonder is the universe continuing to wake. So when you breathe, when you look at the night sky or feel the ground beneath your feet, remember. You are not standing on Earth. You are Earth, remembering itself. And the whispers that began billions of years ago still speak, softly, in everything that lives. The story of Earth is not just a story of stone and fire. It is a story of memory. Every mountain, every ocean, every breath of wind remembers what came before. The stars forged the elements that became the sea gave rise to life, and life learned to dream. Across billions of years, the planet has written its tale in slow, patient chapters. From molten rock to water. From single cells to forests. From silence to song. There were moments of peace and moments of fire. Whole worlds have risen and vanished beneath the same sky that arches above us now. Yet through it all, one rhythm remained, the rhythm of becoming. And now, at the edge of all that time, we listen. We, the newest children of this ancient world, stand awake in its memory. Every breath we take carries the whisper of oceans older than continents. Every heartbeat echoes the pulse that once moved through the first living cell. We are made of everything that came before, the ash of stars, the salt of seas, the dust of comets, the dreams of forests. And in our hands, the planet feels itself again, curious, creative, uncertain, alive. Look closely at the world around you, the curve of a shell, the flight of a bird, the grain of stone beneath your feet. All of it is a continuation of the same quiet miracle, matter remembering itself as life. The earth has never stopped changing, and it never will. The continents will shift, the seas will rise and fall, and new forms of life will emerge to tell their own stories. But for this brief moment, in the span between starfire and silence, we are here, witnesses to it all. The future is not written yet. It waits in the soil, in the sky, in the choices we make. The same forces that built this world now rest in our care. We are no longer just passengers, we are participants in the next chapter of the Earth's becoming. So listen, even now, to the hum beneath everything. It is the same whisper that has always been there. In tides and wind, in heartbeat and breath. The whisper of a planet still telling its story. And when you stand beneath the stars, remember. You are not apart from this world. You are the continuation of its memory. The earth is not beneath you. It is within you. And through you, it still speaks.